project, which was a real dog project, but he did it very well and very faithfully. So in 1978, when we began the program for the new generation of electrolytic materials, the team we put together was myself, Brent Locke, who had never done any zeolite work, Steve Wilson, who didn't even know what a zeolite was, and we started out for about 6 months studying, thinking, and discussing. That's all we did for 6 months. Did an immense amount of literature reading. And we developed a strategy which we call the periodic element strategy. The idea being to have other than silicon and or aluminum in the tetrahedral sites in the three-dimensional microporous frameworks of zeolites. And we had a list that was ranked according to probability of success. And the first two elements that we decided to try were aluminophosphate for a number of reasons. There were many similarities in the structure and chemistry of aluminophosphates versus aluminosilicates or pure silicas. For example, there were quartz, tridymite, and cristobalite analogs in the aluminum phosphate system like those in the pure silica system. There was some hydrothermal chemistry in the literature where various people had reported the preparation of hydrates of aluminophosphates. And there were many other structural analogies. So we started following the concepts that we used in the synthesis of silicolite. In fact, in the very first ideas that were recorded, the material we were going to make was called alpolite, in analogy to silicolite. And I had heard a paper at a colloid conference at Clarkson, whereby they described the preparation of aluminophosphate sol, stabilized sol, much like that of the silica sol that DuPont sells called Ludox. And since we frequently use Ludox to make zeolites and silicolite, I thought that would be a good starting material, and we would add a cation or organic species to template the structure. So that was schematically what you do to make silicolite and high silica zeolite. So we started out that way. We very early on discovered that in the aluminophosphate system, you don't want alkali metal cations because there are innumerable metal phosphates, metal aluminophosphates that are very, very easily crystallized out of aqueous solutions. So we learned that and went on to alkali-free, just pure quaternary ammonium systems. And since tetrapropyl ammonium was the best template for forming the MFI structure, silicolite, we spent a lot of time working with tetrapropyl ammonium and made some structures that appeared to be either dense structures, salt-like structures, or unstable structures, that is, unstable to any thermal treatment. And we were almost about to give up. We used to have meetings a couple of times a week, Brent Locke and Steve Wilson and myself, and we would typically disagree about what the next direction was. And they were usually against me, that is, me with my prejudices in zeolite synthesis. And one of those prejudices that we argued over just before we were about to give up with aluminum and phosphorus was pH. And of course I knew that you could only form zeolites in highly basic systems. So Steve and Brent argued with me and said, well, you don't know, let's try both. So we divided the work, and Steve Wilson had the acid side and Brent Locke had the basic side. The other argument had to do with temperature. And we argued about whether temperature should be higher or lower. So we again divided up the temperature, and one of them took higher temperatures and one of them took lower temperatures. So during the course of that next week, I was in the lab, and Steve Wilson, who was charged with the, I got that wrong, I think Steve had the basic side, Brent had the acid side. Steve had an aluminophosphate system in which he was titrating with a pH meter with tetrapropylammonium hydroxide, trying to get it up to basic. He added immense amounts of tetrapropylammonium hydroxide and appeared to buffer at about a pH 5. And he was about to give up. And he had this gel that he made from pseudobaimite and phosphoric acid and had titrated with a very large amount of tetrapropylammonium hydroxide. The pH was staying at about 5 or 6. And he was going to discard it. I said, no, as long as you made it, let's put it in. So he put it into the autoclave into an oven at 150 degrees centigrade, and indeed he made Alpha 5. And there was a great excitement in the laboratory. We could tell from just the general appearance of the X-ray powder diffraction pattern, number one, that it was novel, and just from the general appearance that it was probably a molecular sieve material. And we very quickly characterized it and learned of its absorption properties, its stability, and so forth. Meanwhile, one of the technicians in the group who had worked with me for many years in the area of zeolite synthesis and the area of high silica zeolite and silicalite synthesis, once he knew how Steve made it, he decided to add silicon. Didn't tell anybody, didn't tell me. Went in the lab, used Steve's so-called recipe, and we now had started to call it the recipe, and indeed made the first SAPO material. And in a very short period of time, we had hired one additional person, Celeste Messina, who had obtained her master's degree in chemistry at the University of Paris. And we immediately put her to work with Brent Locke and Steve Wilson. And with the three of them working in a period of just months, we had discovered over a dozen new Alpha molecular sieves. At that time, word had spread throughout Union Carbide, and we had the vice president of R&D of Union Carbide coming to hear about our work. We were very, very quiet. We didn't write reports. We didn't tell anybody except the group what we'd done. Very secretive. And he wanted to hire 20 PhDs to really get this thing going. I said, no way. 3 years from now, if it's not a commercial success, you're going to have to worry about 20 additional PhDs. I said, but we could use a few more people. So we actually expanded the group either by taking some people who were working in zeolite synthesis and transferring them over to aminophosphate synthesis, or adding some people. And we went back to our strategy and pursued the SAPO, or the silicon aminophosphate materials, and expanded that. We did a great deal of work in that compositional system, and had some 15, 16 structures, very well characterized. Started doing catalytic screening of all of these materials, and there it was very instrumental in developing the materials rapidly that Jules Ribaud, who headed up our catalyst research group, was a real believer in the aluminophosphates and the silicon aluminophosphates. And he set up a small group to do very broad model reaction screening on small quantities of powders, like a half a gram or a gram of material. And almost within a day or two of when we made a new material, if it was pure and we had a good X-ray, it would go down the hall to Jules' group, and he would immediately test it, and we would know which was a potentially good catalyst. And then I, of course, went on to a more developmental application area. We pretty much did the absorption screening ourselves in our group. We had full facilities to determine pore size, pore volume, and so forth. And we realized at this point that we had probably discovered a very major generation of materials. And we decided that there was a high probability that we were going to be able to put more elements, many more elements, into these materials.